Okay, so for the first one here, a caliper. First question, is that metric, millimeter, or inch? It's inches. So where do we start with this one? It's 2 whole inches, 0.5, and then 15, so 2.515 inches. Good. Over here, 2.3, and then 65 comes off the dial, so 2.365. The micrometers. How many whole inches? 0, remember. Tenths would be then 6. And then there's quarters. That is past the quarter, so it's 625. Then what's on the thimble? 1. So we have to add 0.001 to that. So that's 0.626. How about over here? 0.8, 25, 50, 75. And then this is reading 23. So that's 0.898 inches. I'm going to give you a second to read these. We'll talk about those in like 30 seconds. Okay, so for the first one up here, bless you, for the caliper up here, or micrometer, sorry. That is 21.05 millimeters, of course. And this one, 11, 12, 13, it is past the 14 because we have just past 0. What lines up there is 3, so 0, 3, you got it. This one, remember the 1 here stands for 10. We're not there yet. Have we passed the 9? Yes, we've just passed 0, so we have passed the 9. That's 9.12. Yep, 1, 2. It says 12 on the dial. How about this one? $65, $66, $67. 0.47. Anybody have any questions off the calipers or micrometers that we've done? Okay, then it is that time. Let me get this out to you. Okay, we're gonna take a little bit of time and talk about errors and types of error in measurement. So far, we've talked about built-in error in a measuring device. That implied error or possible error that's determined as a property of the measuring device. And it's a property of the measuring scale that's being used. Remember, scale is a term for any time you have those regular markings on something that you're using to measure, like a ruler. A ruler technically is a scale. It's marked out spaces. And that possible error was just 1/2 of that smallest division. That smallest division was the degree of precision. So it was the 1/2 of the degree of precision. In real life, the measuring device isn't the only source of error. There's also human error. There's error caused by conditions and other factors that come involved. There are flaws in the measuring device. One of the most common errors is especially if you're using a hard ruler or even a tape measure, is that the end gets flawed. I mean, a lot of times the end of the ruler, the corners start to get wore off and rounded off, or the end itself wears down. If you're looking at a tape measure, you have that metal piece that's riveted to it. That rivet actually is designed to slide so that if you're hooked over something, it pulls out and you're measuring outside. And if you're inside something, it actually slides in. So that end piece is loose on there, and that's by design. But because it's loose, it moves back and it wears that slot larger over time as it slides back and forth. So there's error that's always caused in there. Generally, it's the end of the ruler measuring device starts to wear out, and it causes that slight error in the measurement. How would you avoid that if you were using a ruler or a tape measure? What would you do to avoid that error created at the end of the measuring device? Well, yeah, always move up. If you have to measure something really precisely and you're using a regular ruler or a tape measure, it's more precise generally to start at the 1 or some other mark rather than 0 and measure from there and then just subtract that from your measurement. Okay, so types of errors we're going to talk about today. Regardless of what the source of that error is, the first type we're going to talk about is called an absolute error. The absolute error is just the difference between the actual value and the measured value. Now I'm going to put subtract in here. It's the difference between them, but I'm going to use a new symbol. Those bars that I just put around it, those are called the absolute value symbol. And it has a deeper meaning in this, but in this case, all it really means is you're looking for the difference between the numbers. You don't care which one's bigger. It's just how far apart they are. So when you subtract them, you're ignoring whether it's positive or negative. You're just looking for the difference between them. The technical definition of absolute value is the absolute difference with no sign to it, positive. So let's say we measure something at 12 and 7/8 inches. Its actual value is 12 and 13/16 inches. If we were to subtract actual minus measured, 12 and 13/16 minus 12 and 7/8 is actually a negative 1/16 inch. So what that's telling us is our absolute error is 1/16 of an inch. Notice I don't worry about whether it's negative or positive. It's just a 1/16 of an inch difference. Next, we have a relative error. A relative error depends on the size of what we're measuring. Relative error is the absolute error divided by the actual value. So in this case, that would be the 1/16 of an inch divided by the 12 and 13/16. Now, if you have fractions on your calculators, it'll be easier for you to do this than mine. But we'll make it work here. We get 0.00488 if I round that off. So that is my relative error. Now, relative errors are often easier to express or more better understood if expressed as a percent error. In fact, some textbooks refer to absolute error, relative error, I should say, and percent error as the same thing. It's just the relative error as a decimal or the relative error as a percent. Some textbooks treat relative error and percent error as something totally different. So just be aware of that as you're working through. There is that relationship between relative and percent error. It's just a matter of terminology as to whether they're considered the same thing or different. Percent error, I'm just going to take this relative error and move the decimal point 2 spots to make it a percent. So that's 0.488%, or about half of a percent error. So is that an acceptable error, half a percent? That's fairly acceptable in most cases. If you got into some precision engine building, it's probably not acceptable, but half a percent is pretty good error. So is that saying a 1/16 of an inch absolute error is okay? Well, not necessarily. What if we have a different situation where your actual value is 2 5/16 inches, and you take the measurement and you get 2 3/8 inches? What is the absolute error? Well, we subtract them again, 2 5/16 minus 2 3/8. Well, that would once again be a negative 1/16. So that's giving us an absolute error of a 1/16 of an inch again. So it's the exact same absolute error. Will the relative error be the same then? No, why not? Well, even though it's still a 1/16 of an inch absolute error, the actual value is only 2 5/16 now. So that's going to be 0.02703. That's the relative error, and as a percent, that's going to become 2.703%. That's probably too big of an error. Why is it a bigger deal to be a 1/16 of an off and the 1/16 of an inch off in this case compared to the one up here? Well, because this is a smaller measurement. We're measuring something smaller. The bigger the object is you're measuring, the further you can be off and still be acceptable. Like in construction, when you're dealing with things that are, 20, 30, 40 feet long, being within 1/8 of an inch is considered acceptable on most applications. Unless you get into cabinetry, then it gets down to the 64th of an inch. And engines, being within a 64th of an inch is not acceptable. I don't know why my computer screen's going nuts on me, but let's see here. There we go. So anyway, the problem is we don't ever know the actual size, the actual value. If we actually knew the actual value, we would have no reason to measure it, would we? No need to measure it if we know what the actual value is. So what we do is for the absolute error, we'll often use that possible error in the measuring device. So for an example, here's my ruler. And I have something that has a reported measurement of 4 3/8 inches. Well, what's the absolute error going to be? What are we going to use as our estimate of the absolute error? Well, let's do this. What's the degree of precision here? 1/8 of an inch. So that means the possible error is what? What's half of an eighth? Plus or minus a 16th of an inch. That's what we're going to use as our, assuming that you use the instrument properly, we're going to assume that's our maximum absolute error. And then we're going to calculate our potential relative error by taking that 1/16 of an inch. Now, normally the relative error would be found by taking the absolute error divided by the actual value, but we don't know the actual value. But we're assuming that the reported measurement is fairly close to the actual value. So 4 3/8 inches. So if I do 1/16 divided by 4 3/8, I get 0.01429, which as a percent is 1.429%, just under 1.5%. What that's telling, 1.5% generally is too big of an error for stuff. Usually they like to stay down around 0.4, 0.5% is the largest errors. So what that might be telling us is that this ruler might not be precise enough to measure something that's only 4 3/8 inches in size. They need to get a more precise ruler. Now, if you get to the other side of it, where rather than measuring items, you're trying to create something. For automotive, maybe you're making your own part, or for dairy, maybe you're trying to find a piece that you can use. If you look at a schematic for something, you see it marked as what does that mean? Okay. Yeah, this 0.750, the 750 thousandths of an inch, is called a desired value. It is sometimes referred to as the ideal value. In an ideal world, in a perfect world, you want that piece to be 0.750 inches, period. This here, the plus or minus, a lot of people refer to that as the tolerance. That's not correct. That's called the allowance. What that is saying is you have an allowance of 5 thousandths of an inch in either direction. So this creates a range just like our measurements do. This is an acceptable range. And just like in our measurement, we go from the desired value, that ideal value, 750 thousandths minus that allowance of 0.005. So that'd be 0.745 inches to the higher end would be the 750 thousandths plus the 0.005. So that's 0.755 inches. So you have a range of acceptable values. Any measurement, if you produce that part and it has any measurement within that range, it's an acceptable piece. Or if you're trying to find a part to use, if it's within those measurements, it is acceptable to use it. The tolerance then is the size of that range. The tolerance would be found by doing the 0.755 minus 0.745, which equals 0.010 inches. That's the tolerance. In most cases, the tolerance is just going to be double the allowance. 0.005 is our allowance, plus or minus 0.005. The tolerance is 0.01. We could have that allowance given as, instead of an absolute allowance like we were given there, we might be given something like this, a relative allowance. Instead of an absolute number of 5/1000ths of an inch, here it's given as a percentage of that desired value. So to find from this relative allowance, to find the absolute allowance, we have to work with our percents. 0.4% is 0.4 over 100. How much is that out of our ideal value? Is that 0.001? So what that's saying is an absolute allowance, this is 0.250 inches plus or minus 0.001 inch. So plus or minus 1,000. And of course, from that, we can get the range. It'll be 2.249 inches to 0.251 inches. Any questions on where that range came from? I know I didn't show any of the calculations on that. That was minus the 1,000th to get this one, plus the 1,000th to get that one. We can work backwards. I could give you the range. I can give you that as my range and ask you to find the desired value the allowance and the tolerance. Well, from this notation up here, the tolerance is easy to find. The tolerance is just going to be the maximum value minus the minimum value. So I subtract the 0.848 minus the 0.836, I get 0.012. That's my tolerance. My desired value is just going to be the average of the two values. That means I'm just going to add them together. 0.836 plus 0.848. I'm going to divide them by 2. Now, one thing to note on your calculator, when you add them together, hit equals first and then divide it by 2. Should give you 0.842 inches. That's my desired value. The allowance is found by taking half of the tolerance. So I take the 0.012 times 1/2 divided by 2, however you want to look at it. That's plus or minus 0.006 inches. So there is my desired value with allowance for that measurement. Any questions so far? Now we're going to get a little bit onto the production side of things for a while, which I know is a little outside the area for either one of the groups in here. But it's something we have to note. If we have something that is marked like this, What's that mean? By 10 thousandths? Okay. It's saying we want this to be 0.450 inches. We cannot be bigger, but we can be a little bit smaller. We can be 10 thousandths smaller. It gives us a range. If I subtract, I get 0.440 inches. To, well, adding 0 means it doesn't change. It's 0.5450 inches. That's the range given. Now, if I had listed like this, 0.445 plus or minus 5 thousandths, that's going to give me a range of the 445 minus the 5, that's 0.440, to the 0.445 plus the 0.005 of 0.450. That gives me the exact same range of possible values. So why would I list it like this instead of this? Well, because neither one of these is saying anything about the ability of the machine you're using to produce it. Like I said, neither one of your groups are in production. I'm not machining, welding, or anything like that. But it's important to know because, well, partly because I have to teach it because this class is used by welding and some other groups that are in production. But it's also important just to understand what it means. This is not talking about the capability of the machine you're using. It's talking about what the part needs to be able to do when you install it, where it has to be installed. Let's say you are operating a machine and you have a machine that's capable of producing within 3 thousandths of an inch. Both of these give you the same range, that you want it to be from 0.440 to 0.450. But this one here is saying if we would really rather have it be right here. That's our target. But we can be smaller but not larger. So with it being within 3 thousandths of an inch, we're going to shoot right here at 0.447 because we want to be closer to that top end. If it were listed like this one, where it was 0.445 plus or minus, well, then we would shoot right at the middle and let them fall where they may around it. So it does make a difference if you're setting up a machine to try to produce these parts. You have to know the capability of your machines to know which way you can cheat. If it's listed as 0.45 or 0.445 plus or minus the 5 thousandths, you're just going to shoot for the middle no matter what. If it's listed as plus 0 and minus 10, then you know you're going to shoot towards one end if your machine possibly is capable of it. Okay, enough of that. We're not going to talk about too much about production. In your book, on page 198, is exercise 4.7, 1 through 41, the odds. Deal with errors and allowances and tolerances.